Hello students, I am Bishwajit Nath. Welcome to my YouTube channel Best Physics Guide by Bishwajit Nath. Today I am going to discuss about the semiconductors and semiconductor devices. You know that according to the conductivity of electricity, we can separate or the materials into three types. First, good conductors. Good conductors are mainly metals are good conductors which can carry electricity better or best, like silver, copper, aluminium, iron, etc. They can electricity in best way, or that's why they are known as good conductors. Next, insulators. They cannot allow to pass electricity through them. That's why they are known as bad conductor or insulators, like paper, felt, diamond, etc. And one is semiconductor. Semiconductors are such material which does not allow to flow electricity through them at lower temperature, but at higher temperature they can allow to pass electricity through them, like silicon, germanium, etc. According to the band theory, we can explain the conductivity of the electricity of these materials. We know that the resistivity of metal or semiconductor changes with temperature. If we plot the resistivity along y-axis and temperature along x-axis, then we find the graph as straight line for a metal. That is, with the increase of temperature, the resistivity increases for metal. But for a semiconductor, the resistivity decreases with the increase of temperature. You know that inside a single atom, the electrons move around the nucleus along some energy levels, and there is a gap between two energy levels. But inside a crystal, there is huge amount of atoms, and that's why the outermost energy levels of an atom can overlap with other outermost energy levels of other atoms, and due to the interaction between the energy levels of the atoms, the energy levels can change from the energy level to energy band. Okay, energy level to energy band, and we can distinguish two type of energy band. One is valence band and one is conduction band. The electrons inside the valence band are attracted by nucleus, and this attraction force is comparatively high. That's why the electrons cannot move freely inside the valence band. That's why these electrons cannot conduct electricity. But in the conduction band, the attraction between the nucleus and the electrons are comparatively low. That's why these electrons can move freely. Therefore, these electrons are known as free electrons. These free electrons can carry electricity, and there is a gap between valence band and conduction band. This gap is known as forbidden zone. Inside the forbidden zone, there is no electron. Since the valence band has minimum energy level and conduction band has higher energy level, therefore the electrons can fill the valence band at the first time. Initially, the valence band is filled by the electrons. Then the electrons can fill conduction band. But when the energy gap between the valence band and conduction band is huge, then the electrons do not jump from valence band to conduction band. But when the energy gap between the valence band and conduction band is small, then the electrons can jump from valence band to conduction band. The energy gap between valence band and conduction band is denoted by Eg. Okay. For an insulator, Eg is greater than 4 electrovolt. That's why the electrons from valence band do not jump to conduction band. Therefore, the free electron density in the conduction band is very small for an insulator. Therefore, insulator does not allow to flow current through them, or an insulator cannot carry electricity. But in case of semiconductor, the energy gap is less than 2 electrovolt. Therefore, at the lower temperature, the electrons inside the valence band do not jump from valence band to conduction band. Therefore, the free electron density in the conduction band is little. That's why at the lower temperature, the semiconductor cannot carry electricity. But at the higher temperature, the electrons inside the valence band can jump from valence band to conduction band to gain some energy or kinetic energy. That's why at the higher temperature, the semiconductors can carry electricity. And when the temperature increases, then more electrons can jump from valence band to conduction band, and the resistivity decreases and conductivity increases for a semiconductor. For a good conductor of metal, the valence band and conduction band overlap with each other. Therefore, the electrons inside the valence band can easily move to conduction band and carry electricity. That's why the metals are good conductor of current electricity. And here the energy gap is almost zero. You know that germanium or silicon has valency number 4. Okay, that is at the outermost shell of electrons of a germanium or silicon atom, the number of electrons are 4. Okay, therefore these electrons form covalent bonds with the other atoms of germanium or silicon. This is the crystal structure of germanium. The blue dots are the valence electrons. These valence electrons are bound to each other by covalent bond. This germanium atom has 4 1 2 3 4 1 2 3 4 4 valence electrons, and this germanium atoms also 4 valence electrons. These 1 valence electrons share by each other, and that's why the outermost shell can fill by 8 electrons. 1 2 3 4 5 6 7 8 electrons. Okay, and in this way they form covalent bond. This is the crystal structure of germanium. At the room temperature or low temperature, there is no free electrons which can carry electricity. That's why at the room temperature or low temperature or room temperature, germanium cannot carry electricity. But at the higher temperature, when the valence electron absorb some heat energy, and due to this heat absorption of heat energy, kinetic energy of valence electron can increase, and that's why the valence electron can break the covalent bond and move and becomes free electrons. Okay, therefore this valence electron can free and becomes free electrons. Okay, therefore there creates a gap. This gap is known as hole. Since this space was electrically neutral, but after removing an electron, this space becomes positively charged and lack of electrons, and this is negative electron. Therefore we can consider this hole as positively charged, and this positive charge is equivalent to the electron, and electron has charge minus 1.6 into 10 to the power minus 19 coulomb. Therefore a positive hole has charge 1.6 into 10 to the power minus 19 coulomb. Okay, now this free electron can carry current electricity. On the other hand, these free holes can also carry electricity. When we apply an external electric field in the crystal, that is, here it is positive, here it is negative pole, and it is positive pole of an external electric field, then this positive pole attracts the free electrons, and these free electrons then move to the positive pole. Now due to the negative pole, this electron is repelled and it jumps, or this electron is repelled and it jumps to the hole, positive hole. Therefore this hole is fulfilled by an electron, and here new hole is created. Now this electron can move to this hole and fulfill, and here new hole is created. Therefore when the electron moves from negative to positive pole of an external electric field, then holes move from positive polarity to negative polarity of the external electric field. That's why we can say that for a semiconductor there are two types of charge carrier. One is free electrons and other is free holes. This is the intrinsic semiconductor, that is, it is the pure semiconductor. Due to the lack of free electrons or free charge carriers at the lower temperature or room temperature, we can increase the free charge density inside a semiconductor by doping. there are two type of extrinsic semiconductor or impure semiconductors. One is n-type semiconductors and other is p-type semiconductors, where the free electrons density is more than free holes. Then this type of semiconductor is known as n-type semiconductor. And where the free hole density is more than free electron density, then this type of semiconductor is known as p-type semiconductor. When pentavalent some atoms or some elements can mixed with the pure semiconductors by a little amount, then these impure elements can mixed with the crystal of the semiconductors. In this way we can get n-type semiconductor. Here we can mix phosphorus with the germanium. The amount of phosphorus is very small, and that's why the phosphorus can place inside the crystal structure of germanium. Okay, we know that phosphorus has 5 valence electrons, but a germanium has 4 valence electrons. That's why a phosphorus atom has one more valence electrons, which cannot participate to form the covalent bond. That's why this extra electron can move freely. This extra electron can increase the number of free electrons. Therefore, at room temperature, this type of impure semiconductor can carry electricity. This type of semiconductor is known as n-type semiconductor, because here the number of free electrons is more than number of free holes. When the temperature increases, then the number of free electrons as well as free holes also increases, but the number of free electrons always be greater than the number of free holes. That's why this is known as n-type semiconductor. When we use aluminum as the impure material or impure elements, then this will be the p-type semiconductor. You know that an aluminum atom has 3 valence electrons, but germanium has 4 valence electrons. When we mixed very little amount of aluminum with germanium, then aluminum can place itself inside the crystal structure of germanium. Due to the lack of one valence electron of the aluminum, there will be an empty space in this covalent bond. This empty space is known as hole. This hole can carry electricity at room temperature. This is the free hole which can carry electricity at room temperature. That's why it is known as p-type semiconductor. When the temperature increases, then free holes as well as free electrons increases, but the number of free holes density is always greater than the number of free electron density. That's why this is known as p-type semiconductor. By mixing the impurities with the semiconductor, we can increase the conductivity of a semiconductor. This process is known as doping. Next, PN junction. When we doped a semiconductor crystal, one side by p type or another side by n type, then it is known as PN junction. This is a single semiconductor crystal. One side is doped and it is converted into p-type semiconductor, and other side is converted into n-type semiconductor. Okay. Here these rounds or sub-rounds are known as free holes H plus, and these dots are known as free electrons. But due to the diffusion, the free electrons moves towards the p-type junction. Since the mobility of free electrons is greater than the mobility of free holes, that's why due to the diffusion the free electrons move from n-type to p-type junction. Okay. Therefore, this n-type region loses some free electrons, and this p-type gains some free electrons. Therefore, here the negative charge density increases and here the positive charge density increases. Okay. Therefore, p-type semiconductor gains some negative charges and n-type gains some positive charges. After some time, this diffusion stops. Because these free electrons repel to come other electrons from n-type to p-type, and due to this repulsion of the free electrons in the p-type stops this diffusion, and there is a region. This region is known as depletion region. In the depletion region, that creates a potential difference. This potential difference have a potential difference small v. Okay. This depletion region has some potential difference. This is denoted by small v. When this p-type PN junction is connected with an external electric cell whose potential difference is more than small v, then again charge can flow. When the p-type is connected with the positive pole of the external cell, electric cell, and the n-type is connected with the negative pole of the external cell. Here V is the potential difference of the cell. Here capital V is excessively greater than small v. Here capital V is potential difference of the electric cell is excessively greater than the potential difference in the depletion region. In this case, this positive pole of the cell can attract the free electrons which stored inside the n-type region. Therefore, the free electrons can pass through n-type to p-type, n-type to p-type. Therefore, again the flow of charge occurs This flow of charges produces to flow of current electricity. Therefore, when the p-type of a PN junction is connected with the positive pole of an external cell and the n-type is connected with the negative pole of the external cell, then current can passes through the p-type junction to n-type junction. This is known as forward bias. This is known as forward bias. This current flows due to the flow of free electrons and free holes. Here I is the total current is equal to IE plus IH. Here I is the current flows due to the free electrons and IH is the current flows due to the free holes. Here the free electrons inside the n-type semiconductor are known as major charge carriers and the free holes inside the p-type semiconductor are known as major charge carriers. That is, free electrons and free holes are the major charge carriers for n-type and p-type respectively. That is, for n-type charge carrier the major charge carriers is free electrons, and for p-type semiconductor the major charge carrier are free holes. And this type of connection or bias is known as forward bias. Therefore, in the forward bias or FB, that is forward bias or FB, current can passes through the circuit. That is, in case of forward bias, current passes through this circuit. Okay. In case of forward bias, the width of the depletion region decreases. Width of the depletion region decreases. Okay. When the p-type is connected with the negative pole of the external cell and n-type is connected with the positive pole of the external cell, then the width of the depletion region increases. Width of the depletion region increases. In this case, the flow of current through this circuit is very negligible, that is almost zero. This is known as reverse bias. In this case, small amount of current flows due to the minor charge carrier. Here, positive holes, free holes inside the n-type semiconductor is minor charge carrier, and inside the p-type semiconductor the negative free electrons are the minor charge carriers. And due to the minor charge carriers, small amount of current flows through this circuit, which is negligible. That's why it is known as reverse bias. Therefore, we can say that a PN junction can allow to flow current when p-type is connected with the positive pole of the battery and n-type is connected with the negative pole of the battery. And when the p-type is connected with the negative pole of the battery and n-type is connected with the positive pole of the battery, then this PN junction does not allow to flow current. This is reverse bias. That's why the major current can flow through p-type to n-type, p-type to n-type of the PN junction. That is, the flow of current through PN junction is unidirectional. That's why PN junction is known as diode. That's why PN junction is known as diode. We can plot potential difference versus current graph. Along x-axis, we plot the potential difference of V. Along y-axis, we plot current. Here, the forward bias graph, V increases and with the increase of V at the positive direction, the current also increases. Here current is plotted in milliampere scale and the voltage or potential difference is plotted in volt unit. At this point, the current increases in accelerated way. This voltage is known as knee voltage. After knee voltage, the rate of increase of current is huge. When in the reverse bias, when the potential difference increases at the negative pole, but the current, reverse current, does not increases. This graph is almost parallel to the negative x-axis. Here the current is plotted in microampere scale. That is, the amount of current is very small, although the potential difference is huge in the reverse bias. But increasing the potential difference at a certain voltage in the negative polarity, the reverse current suddenly increases. This phenomena is, or this effect is known as Zener effect, and this voltage is known as Zener voltage, and it is denoted by Vz. In case of Zener effect, the negative potential or negative electric field is huge. In this case, this negative potential or negative electric field can break the covalent bond and it can release huge amount of free electrons and free holes. That's why at the Zener voltage or more than Zener voltage, huge amount of reverse current increases. This phenomena is known as Zener breakdown. We can use PN junction as a voltage rectifier or current rectifier. That is, we can convert AC to DC. That is, we can convert alternating current to direct current by a PN junction. This is the circuit diagram of half-wave rectifier. This process is known as rectification. This is the circuit diagram of half-wave rectifier. Here, this is the input AC or input alternating current or alternating voltage. This is the transformer, and the output circuit is connected with a PN junction, and this is the load, and RL is the load resistance and IL is the load current. This is the graph of an alternating voltage. It is the sinusoidal graph. When the P type is positive and N type is negative, then only the current can allow to pass through the output circuit or load circuit. But when the P type is connected with the negative pole and N type is connected with the positive pole, then current does not allow to pass through the load. That's why we can get only half circle at the output. That is the positive cycles, positive half at the output. This is the potential of the output voltage. This is the graph of the output voltage versus time. Here along x-axis we plot time and along y-axis we plot the output voltage. Okay. In this case, the P is positive and N is negative. That's why current can flow through the load line, and when in this case the P is negative and N is positive, in the P type is negative and N type is positive, in this case we cannot get current at the output. Therefore, we always get the positive currents, positive potentials at the output voltage. Therefore, in the output circuit, it is positive pole and it is negative pole. That's in this way we can convert the AC into DC. This current or this voltage is known as ripple voltage. But due to the half wave rectification, we lost 50% energy. That's why we use full wave rectifier. Here, two diodes D1 and D2 or two PN junctions D1 and D2 are connected parallelly. D1 is the first diode and D2 is the second diode. Between them, the load resistance or load is connected parallelly, and this at the midpoint, this is the midpoint of the circuit or coil. When the first half, that is D1, is positive, then D2 is negative. That's why the current, when the, in this case D1 is, then in this case the P type of the D1 is positive and the P type of the D2 is negative. Therefore, in this case, current flows through D1 to the path A, B, C, D or A, B, C, O. Okay. But in the next half, the P type of D1 is negative and P type of D2 is positive. In this case, current flow through the OEFCO. Therefore, in the output circuit, we always get the current from C to O. That is, the load current is unidirectional from C to O. This is the graph of output voltage versus time. Here we can get full cycles. That's why it is known as full wave rectifier. Here the current is always in unidirectional. That's why the output current is known as direct current, or voltage is known as direct voltage. And this direct current or direct voltage is known as ripple voltage or ripple current. In this way, we can convert AC into DC by full wave rectifier. This is the circuit diagram of bridge rectifier. When the N type of D1 diode is negative and P type of D2 diode is positive, then current flows from D2 to A to B to D1. Therefore, current flows through the load from A to B. When the P type of D2 diode is positive and the N type of the D3 diode is negative, then current flows from D2 to A to B via D3 diode. That's why in the load, the current always flows from A to B. Therefore, we always get the unidirectional current or DC current in the load line. In this way, by bridge rectifier, we can convert AC into DC. So, I am going to complete my video for today. Please subscribe my channel. Thank you for watching my video. Have a nice day.